Great. So I'm James, and thank you for the introduction and for the invitation to talk to you today. If you could mute your microphone, that'd be good. So I'm coming to you today from my home in New Zealand. I'm sorry I couldn't attend. Our borders are still closed due to COVID. So today I'm going to present a brief review of some of the phenomenological models used to describe the pseudogap phase in underdoped cuprates, which dominates the underdoped region of the phase diagram and often shown to terminate just below 0.2 holes per copper. Obviously, we know now the phase diagram is more detailed. For example, there is a region of superconducting fluctuations just above the TC dome. And as a result, the superconducting gap will persist into this region, giving the appearance of a pseudogap. As talked about earlier, there's also a region of charge ordering near 1/8 doping, which becomes stabilized at high fields. I won't be talking about that today. I'll be talking about this pseudogap phase seemingly arising from some sort of coexisting order parameter. So the first evidence for the pseudogap came from these NMR measurements where a downturn is observed in the NMR night shift as doping is reduced, signifying a gap in the spin degrees of freedom. These later measurements on the right show that the downturn sets in just below 0.2 holes per copper in YBCO. Sure, I don't need to tell anyone here, but to revise, obviously a superconductor is characterized by an energy gap that closes at Tc. If we multiply the density of states by this thermal window function and integrate, we get the electronic entropy, which exhibits a change in slope at Tc, and therefore we get a jump in the derivative at Tc, which is the specific heat jump. Obviously, in cuprates, the gap has a D-wave symmetry, so linear dependence about the Fermi energy, which gives rise to a linear temperature dependence in the specific heat. So here is John Lorem's classic data for YBCO. In the overdoped region, the specific heat jumps are nice and large. The underlying specific heat is relatively flat, and the entropies almost coincide. And this suggests that the density of states in this region is roughly independent of energy and doping. However, as we move into the underdoped region, the specific heat jump collapses, which we can plot on our phase diagram. There is a downturn like in the NMR in the normal state specific heat, and there is a persistent loss of entropy right up to the highest temperatures that we measure. So this suggests that the pseudogap itself is temperature independent. We can model these features by a second energy scale, the pseudogap energy, which obviously proceeds like so. Specific heat tells us that the pseudogap is fundamentally different to the superconducting gap, where the superconducting gap is states conserving, meaning that the in-gap states get transferred just above the gap edge into these coherence peaks. The specific heat and the loss of entropy suggests that the pseudogap is non-states conserving, meaning that we're transferring these states or spreading them out over a much wider energy range. John modeled this using a triangular cutout in the density of states shown by the dotted line, and this gives rise to a reduction in the specific heat jump, a smooth downturn, and a persistent loss of entropy, consistent with experiments. So specific heat, a bit like Raman, doesn't tell us about the momentum dependence. So for that we need momentum resolve technique. This is what we expect the overdoped electronic structure to look like. And obviously the Fermi surface is that region separating occupied from unoccupied states, and is hole-like because it encloses the unoccupied states. In 1998, angle-resolved photo emission showed us that the pseudogap opens near the zone boundaries at the so-called antinodal regions, leaving these ungapped regions of Fermi surface come to be known as Fermi arcs. Possible explanations for these arcs are that they are thermally broadened point nodes, or that they form one side of a closed pocket. So our triangular gap model evolved into a Fermi arc model where we can now specify the size of the Fermi arc using this angle parameter. And the finite Fermi arc gives rise to a residual density of states at the Fermi level. So our gap is no longer a complete gap, it's more of a depletion, hence the name pseudogap. Below TC, the superconducting gap opens up on these ungapped regions, giving rise to a kink in the gap structure, similar to what is seen in some of the tunneling work. Now, in this two-gap picture, the pseudogap removes states of the Fermi surface that would otherwise be available for superconductivity. As a result, the effective superconducting gap is reduced, and this leads to a weakening of superconducting properties such as the superfluid density. This two-gap picture does quite well at explaining Raman spectra, the work shown by the first presenter, and can explain the so-called nodal-antinodal dichotomy. So if we select a B1G polarization where we're probing around the antinodal region, what we find as doping reduces as the peak in the spectra shifts to higher wave numbers, as shown here, due to an increase in pseudogap magnitude. Whereas in the B2G polarization, where we're probing around this arc region, the peak in the spectra shifts to lower wave numbers due to a shrinking of the Fermi arc and a reduction in the effective superconducting gap magnitude. Now, the problem with a Fermi arc model is that a Fermi arc breaks the definition of a Fermi surface. It no longer encloses occupied or unoccupied states, and the discontinuities at the edges pose problems for calculating transport properties which depend on the derivative of the electronic structure. And so one way around that is to, of course, assume that the arc is one side of a pocket, leading us to these Fermi surface reconstruction models, of which two examples are shown here. So in these models, the large hole-like Fermi surface in the overdope region transforms into these small pockets near the nodes, and there is an intermediate region where we also have electron-like pockets near the antinodal region. These two models are quite similar, the main difference being that in the spin density wave reconstruction, we're simply folding the zone along the diagonal, and hence the pockets are symmetric along that diagonal line. And there is some limited photo emission data in support of both of these pictures. So this animation shows the reconstruction of the electronic structure. As we switch the pseudogap on, I'll be largely focusing on the YRZ model, the resonating valence bond spin liquid model proposed by Yang, Rice, and Zhang. So in this model, the nodal hole-like pocket is caused from the lower branch here poking through the Fermi level. while those electron-like pockets near the antinodal region are caused by this upper branch starting to rise through the Fermi level. Some key features to note are that in this picture, the pseudogap first appears entirely below the Fermi level. Also, as the electron-like pockets begin to disappear, the pseudogap then begins to span the Fermi level. Note too that, as mentioned by our last speaker, there's a particle-hole asymmetry in the pseudogap. And furthermore, this gap appears to be non-state conserving, so it has that property which would describe the specific heat also. The particle-hole asymmetry becomes relevant when we want to look at thermoelectric power measurements, because that observable is sensitive to asymmetry in the electrical conductivity about the Fermi level. So put simply, if our conductivity below the Fermi level is larger than the conductivity above the Fermi level, we'll get a positive thermopower and vice versa. And the energy range that we add to our scales here depends on temperature. So if we calculate this thermopower from the YRZ model, remembering that at the onset of the pseudogap it appears below the Fermi level, this leads to an undulation or a down-up-down temperature dependence in the thermopower. There's a very subtle hint of it in the data points, and note that this corresponds to a very high doping, near 0.25. And I'll come back to this point shortly. Another property that is sensitive to this sort of reconstruction is the Hall number. So the Hall number is a measure of the carrier density, and strictly speaking, for a circular Fermi surface is proportional to the area enclosed by the Fermi surface. So in overdoped cuprates, we have a large hole-like Fermi surface enclosing 1 plus P holes per copper. The 1 comes from the fact that the copper atoms are half filled and so have 1 hole associated with them. In the underdoped region, the smaller pockets are proportional to P holes per copper. If we calculate the Hall number from this Fermi surface reconstruction, we could see that the Hall number transitions from 1 plus P down to P, and it is accompanied by this transition region here, which corresponds to the dopings where the electron-like pockets are present. So in the same year I did this work, these nice high field measurements were done by Louis Teifer's group, and high field experiments are really proving to be a great way to expose underlying normal state behavior. And as you can see, they reported a very similar transition in the Hall number. If you overlay those data points, there's almost an exact match. And this to me is the best support yet that the pseudogap arises from some sort of reconstruction like this. But how else can we test this picture? So a feature of this sort of model is that it predicts a separation between the doping where Hall number changes and specific heat changes. So in this work, they showed, as I did, that at the onset of reconstruction, the Hall number decreases, whereas if you look at the specific heat jump at TC, that doesn't change to a lower doping. So they call the upper change P star and the lower doping here PE. And this corresponds to the region where the electron-like pockets start to vanish. So between 0.15 and 0.17. This becomes very interesting because of more recent work done by the team at Bristol, who report high field Hall number measurements for thallium-2201 and bismuth-2201. Note that the change in Hall number appears at a much higher doping than traditionally seen for the pseudogap around 0.2. And in bismuth-2201, it's particularly high, corresponding to the edge of the TC dome. We can, of course, model that in the YOZ model simply by changing the onset doping of the pseudogap, so that's very simple. And it's interesting to note too that, as I mentioned earlier in the thermopower, that this is where we predicted electron-like pockets, so there's a nice consistency there. It would obviously be good for thermopower measurements to be repeated on crystals. I think I've got 2 minutes or so. So let's just look at some other properties. Here is the superfluid density measured by μSR at 0 temperature. We could plot that on here. And also the specific heat jump for thallium-2201, which we can also overlay. Note that both properties will have to undergo some sort of maximum near a lower doping around about 0.18 or so, far below the onset of the change in Hall number. This change or decrease in superfluid density and specific heat is not expected in BCS theory and is believed to be due to an increase in pair breaking as we increase doping. If we add pair breaking to YRZ, it's possible in fact to push that maximum and specific heat jump down to lower dopings. Note that here is where we have the reconstruction occurring. If we increase pair breaking, our maximum and the specific heat jump can be pushed to lower doping, seemingly consistent with the experiments. I've talked about YRZ, but spin density wave reconstruction is a good candidate also. Obviously, the question is what could be driving this sort of reconstruction. The spin density wave reconstruction offers a nice symmetry with electron-doped cuprates, for which there is some evidence for that sort of reconstruction. Also, there was some nice ARPES results published on this 5-layer system where the innermost planes seem to exhibit a symmetric hole pocket consistent with spin density wave reconstruction. Running out of time here, but what determines P star? It seems to depend on the family of cuprate. Does it have a dependence on band structure parameters? And I'll skip this and go to my summary. So thermodynamics tell us there's a loss of states near the Fermi level. Spectroscopy tells us that it's an antinodal gap. And lastly, transport measurements tell us that this could be due to a Fermi surface reconstruction into small pockets. So thanks for your attention.
Thank you.
Yes, thank you, James, for this very nice talk. I have a question for you. With your reduction, if I understood, it's based on antiferromagnetism and spin density wave. Can you explain the backbending? It's a bit technical, but from what you present, I think you will know exactly what I'm talking about. The backbending of the dispersion energy observed in bismuth-2201. So according to Patrick Lee and others, you need some kind of particular symmetry, some kind of pairing in order to have this bending.
Yeah.
Do you agree with that, and how do you account for it in your model?
Yep. So can you see this slide? 1 second. This one. So Both models, Yang, Ice, and Zhang, and the spin density wave reconstruction give you the separation from the Fermi wave vector due to this particle hole asymmetric gap. So if that was what your question was about, it appears to be consistent with antinodal photo emission.
But to get the backbending on the right side here, you need particle hole, some kind of breaking of particle hole with particle.
Yes.
So effectively your model also takes that into account.
Yes.
So you have some kind of preformed pairs hidden there.
Potentially, yes. Superconductivity obviously occurs on top of this model. So, yeah.
Okay, thank you.
May I ask a question?
Sure.
Excuse me, may I ask a question?
Yes.
Do you hear
Go
me?
ahead. Yes.
How do you explain your approach that in quantum oscillation measurements, whole Fermi surface is not observed under doping? They see only Fermi pockets.
Yes, so I have a slide there too, I think. So a lot of quantum oscillations measurements are done near 1/8 doping in this charge-ordered region. And it's been suggested that there are electron-like, diamond-like pockets which would explain those measurements. It's possible that the high field is adding a further reconstruction of these small hole pockets into this diamond-like pocket. So that sort of evolution of the Fermi surface is how I understand things at the present stage.
And what about the volume of the electron pocket? Is it about 2 or 8% of the beryllium zone, or is it large?
Yes, it is about that size.
Thank you.
Yes, I have a question.
Other questions?
According to you, what is the origin of the asymmetry of the pseudogap?
Oh yes, so that depends on the particular model that's used, but all of these models are similar in the sense that if I go back to this plot, they all give you this asymmetric gap, and the reason is sorry, I'm jumping around a bit. 47 is the slide I want. Whenever you have this reconstruction that takes this form, this can be the YRZ term, or it can be K plus pi. You will get this sort of asymmetric gap, even in a charge density wave case also.
Thank you.